All right, welcome everyone. This is discussion 14. Before we get started, just want to make sure, am I audible to everyone? Because we have very few people today, but am I audible right now? Okay, all right, so we'll proceed. Before we proceed, just have an apology. I had to cancel my office hours yesterday. I was not feeling well. But if you have any questions about the project or the course or anything going in the class, feel free to email me and we can set up a convenient time to meet. My office hours are now moved to Friday. So instead of Tuesday this week, I'll be meeting on Friday between 3 and 5 California time. The second announcement is about the course project. So you must have already received my comments on your proposals. Most of you did a pretty good job at figuring out what data set you're going to use. Some interesting data sets came out, which I had not assumed. Uh, the only thing that I wanted to point out was in some cases, if you're doing the ANOVA analysis, the entire premise of doing ANOVA is you're working with not two groups, but you're working with more than two groups, right? If you just have a problem which has only two groups, so we have one categorical variable, and this categorical variable has what we call two levels. If we have two levels, uh, or two groups, then ANOVA is not really required. You can just do like a paired t-test or an unpaired t-test or a non-parametric version of it. The reason we were using ANOVA is because we have more than two groups, right? So if you have chosen a data set which has a categorical variable and a continuous variable, but the categorical variable does not have more than two groups, it has only two groups. So let's take an example of, let's say, sex. So if sex is only male and female, that means it has only two groups. Doing an ANOVA on this is equivalent to doing a t-test, okay? But we specifically want you to do one-way ANOVA. So you should choose a data set which has more than three groups, okay? So the way the grading is going to work out is this particular part one, the grades that you got are not going to affect your final grades, okay? This is just meant as a pointer to point you in the right direction of what data set you should be choosing. So if you got less than 10 points, don't worry about it, okay? The final project which you turn in, which is part two, will be the only one which will be graded. But make sure if I've given you comments about what is probably not so right about the analysis, then you pay attention to that. So we'll not again go over reviewing your part one. We'll now just do it as part of part two. So once you turn in your part two submission project, then it should have all the components fixed. Okay, so in the previous version, if you were just working with a data set which had one categorical variable and two groups, then make sure you either change your categorical variables. Some data sets will have multiple categorical variables. So you should ideally be picking up that particular categorical variable, which has at least three groups. Okay. In the other case, if you have a sample, if you have a data set for which the categorical variable has only two groups, then it might be a better choice to go with a different data set. There's no lack of data sets that you have, so you will have enough choices to make. Okay. All right. So the other concern I had was, uh, I think Peter has already mentioned this in the R assignment and in the R tutorials that he goes over with you. So sometimes you load the data sets, some of the categorical variables in the data sets are encoded as numeric quantities. So for example, one way to encode sex is one and zeros, right? So one represents, let's say, male and zero represents females. But when you're doing this analysis in R, you want a way for this to be interpreted as what's called a factor in R. This factor essentially makes R understand that this is not a numeric quantity, but a categorical quantity. Okay, so let me share my screen and I'll just quickly go through what I mean by that. So, okay, so hold on. Okay, so I'm going to stop my video. So what essentially I was talking about is, so I'll just use this space to talk about it. So let's say you have sex. And in your data set, it's encoded as 1 or 0. Okay, so if you read your data set as read.csv xyz.csv, then I want to ensure that my sex column is interpreted as a categorical variable. So you need to be able to do this, okay? Peter has an example about this in the R assignment, in the R tutorials, but I just wanted to go over it, okay? Because you might be facing this issue. If I want to, let's say, make the box plot of, okay, this is first of an example of just two categories, but you will obviously be working with categories which are more than two. So if you want to plot a box plot, the first step that you need to make sure is your categorical variable is definitely a categorical variable, okay? And the way you do that is to make sure that this is interpreted by R as a factor, and hence you use as dot factor, okay? In some cases, let's say the numeric quantity associated with it was, let's say, GPA. So this should be numeric. Sometimes what happens is if the entries for some of the GPA rows are missing, then sometimes R interprets this as a string or as a factor. But we will essentially also ensure that this gets interpreted as a numeric quantity. Okay, very simple. There's nothing complicated about it. It's just making sure that the corresponding columns get interpreted in the right way. So this is for categorical, and this is for numeric. Okay. So make sure you do these steps before you do the rest of your analysis. Otherwise, in some cases, you might get errors. Okay. In some cases, you don't need this particular step, the numeric step, because it's already interpreted in the right way. But it still wouldn't harm you if you do it this way. Okay. If you're facing any errors, one possible likely origin might be that the categorical variables are not being interpreted as categories. Okay. Okay. Hopefully that's clear. The other comment I had was again about ANOVA. So ANOVA requires continuous data. Okay. So if you're working with counts data, so let's say number of children, number of cells, etc., then ANOVA is probably not the right choice for it. Okay, and the reason is because this data is not continuous, it's discrete. And the assumptions about continuity and normality are not satisfied for discrete data. So if you're choosing your count data for doing ANOVA, make sure you move it to, you choose a different variable, because the assumptions, so you can still run ANOVA on it, but the results are not going to be trustworthy. Okay. So that's the other thing that you need to be aware of. So that was about the project. Are there any questions about the project? Okay, if not, then I'll proceed with the discussion. So the discussion today talks about linear regression. This will probably be our last discussion where we talk about new things. In the next discussion, we might be doing a review, because this is the last week, kind of the last week for classes. You have a review session in the next Tuesday session, which is also the last day of the classes. Okay, so the first square problem essentially deals with calculating the correlation coefficient. What you're seeing here, let me zoom it a bit, is a scatter plot where the x-axis shows the horsepower and the y-axis shows you the qsec. Qsec is essentially the amount of time or the number of seconds that it takes to speed up to 1/4 of a mile. So another thing that you notice is this is again in some sense counts data, right? Because this is again discrete and this is discrete again, but you can still calculate correlation coefficient. The kind of structure that you would see in such scatter plots where both the quantities are counts is in some sense a bit more structured than what happens in a continuous, if both the variables are continuous. And the entire reason is because if you see continuous quantities, then they can take all possible values on the x-axis. However, if it's X, it can only take, if it's discrete, it can only take discrete values. Okay. And this gives rise to certain structure. Okay. So this is discrete. Okay. So in some of your projects, I've left a comment that if you're working with discrete data, trying to do a regression, then you might see a distinct structure. Just be aware of it. Okay. There's nothing wrong about it. Just be aware of it. Okay, so the first problem, given the scatter plot, do you expect the correlation coefficient to be positive or negative? Okay, anyone wants to take a hit at this problem? What do you think is the direction of correlation? Yeah, so it should be negative, right? So that's perfectly all right. So we have this particular slope direction. As x quantity increases, the y quantity decreases, or vice versa. And hence, this is negative. One more note about what's plotted. So generally when you're plotting, X is your independent variable, okay? And Y is your dependent variable. So in some sense, we are saying that Y varies with respect to X, okay? However, when we calculate the correlation, it does not matter whether you're calculating the correlation of X with Y or Y with X. It's essentially equal, okay? So this is negative. The next problem asks us to calculate if the uh, point which has 100 horsepower, which has a Q-sec of 23, which happens to be this point here. If I were to delete this point, why am I deleting? That's just because this appears to be an outlier. So if I delete this point and instead add a new point somewhere around this, because I'm reducing the value to be 20, this is your new point, then what would happen to the magnitude of the correlation change? What do you think would happen if I were to remove this red point and replace it with the blue value? Should the correlation coefficient increase, decrease, or should it remain the same? Yeah, so it should increase the strength, right? So overall, this particular point, the red point, is in some sense negatively affecting my correlation. Why so? Because it seems to be an outlier, and hence at a particular value of, if you are in this range of horsepower, then you expect the correlation, the particular y values to be lying around somewhere in this domain. But this point is, the red point here is an outlier, and hence it's kind of negatively impacting the absolute magnitude. Okay, so the absolute magnitude can be consistent. So the absolute magnitude will increase. And notice that I'm mentioning this to be an absolute magnitude. That's because the correlation coefficient, if I was working with negative, if this outlier point, if it was, let's say, 0.9, then with the blue point, it's going to be around 0.95. Okay. So if you think about in terms of the actual value, then this actual value has reduced. Okay. 0.95 is lesser than 0.9, but the absolute magnitude, that's the absolute value of this correlation, that has increased. Okay. All right. So move to problem C. Problem C gives us a bunch of values and it asks us to calculate the correlation coefficient. This is a very simple exercise. I'll first write down the formula and then I'll explain why it is the way it is. So in some sense, the correlation is capturing your ability to predict the other value, given that you know one of the values. Okay, so if you know the values of x, in some sense, is trying to predict what the value of y would be. So we use this space. So R is always restricted between 1 and -1. It also it includes 1. So a perfect value of 1 implies that y can be predicted exactly from the values of x. Okay, so there's one-to-one correlation between what there's exact similarity between what the value of y is and what the value of x is. The formula, on the other hand, can be explained by this fact that you're accounting for this term on the numerator is called the covariance. It's not exactly the covariance, but I'll explain what that means. And it's so you're essentially capturing how much can x and y together deviate from their respective means after having accounted for their respective standard deviations. Okay. And that's essentially how it's essentially trying to tell you that how closely can you predict one value of x given that you know the value of y and vice versa. So all you have to do in this particular problem is just plug in the values. And if you plug in the values, then you get a negative number, 0.707. And you can see why this number is going to be negative because the numerator term is negative. And this also matches our intuition of the correlation actually being negative. And here is the number of points. So the total number of points here are 32. So n is 32. Okay. Problem D. Using a threshold of alpha, test if the correlation coefficient is significant. So you can always calculate the value of a correlation coefficient. However, we don't know if we can, in some sense, rely on it or not. So that's why we have also a statistical significance attached to this particular value. Now, what does it mean to attach a statistical significance value to correlation coefficient? So let's take this scenario where you have certain data points lying along this, and they are also, let's take it here. So in some sense, there are two clusters of points. So you can imagine that the correlation is going to be positive. There's no doubt about it. However, there seems to be a lot of variance in, sorry, not in this direction. There's a lot of variance in this direction. Okay. So in some sense, the SX, the standard deviation of X is, so that because there is a lot of variance in terms of the values itself, the correlation coefficient significance is going to be less. Okay, what does it mean? It's particularly, it means that the p-value is going to be higher. And why so? Because even though we have evidence of the correlation going in a particular direction, we do not have enough data points to be able to tell whether we have estimated the correlation coefficient in the most statistically significant way. If you, on the other hand, if you increase, if we had just more points lying along this direction, then the statistical significance will definitely go up. Okay, the correlation coefficient might still remain the same, but given that you have lesser variability now because you see a lot of clustering which is homogeneous, that's why your significance in this case might, so I'll just use a different color so that, so I'm still able to get the same correlation coefficient, but in this case my significance is higher. Okay, that's like the intuitive meaning of being able to attach significance to the correlation coefficient. In terms of what the formula looks like, so it also follows the t-statistic, and it's given by this particular formula. So one clear thing that you can see is if you increase the number of points, then the t-statistic would go up. And the moment you realize your t-statistic is going up, that generally means that your p-value is going towards the level of significance. The degrees of freedom for this particular distribution are given by n-2, which happen to be 30 here. And if you calculate this value, this comes around to be minus 475. Okay, we already know the value of r. It's going to be negative because r is negative. We already know n and the denominator as well. Now, if you go to table 4, let's go down. So table 4, degrees of freedom 30, we look for this line. We look for a value of 5.7. Again, remember, recall that your value was minus 5.7, but these values are all positive. So we'll look for its absolute value. And hence our p-value is definitely less than point. Sorry, there is one more zero. Okay. Now, I did not specify the alternate, but the alternate by default generally for the hypothesis that's being tested. So your H naught is R equal to 0, your HA is R not equal to 0. And hence the p-value that we get needs to be multiplied by 2. So p is less than 0.01. And at alpha equal to 0.05, we reject H naught. In some sense, we are saying that we have enough evidence to reject the null, saying the null which says that the coefficient is 0. The correlation coefficient is 0. Okay, we'll move to part E. And this is an interesting problem, which I'm sure most of you will be, actually maybe all of you will be able to figure out, is the car manufacturers are now interested in whether manipulating the horsepower can alter the Q-sec. Okay. From the data that you have, can you use the data that you have to answer this question? So what data do we have? So we have this data that R is minus 0.707. The P is less than 0.001. So with this information, can you say that the horsepower can be used to manipulate Q-sec? This symbol implies manipulation. So if you want some sort of Q-sec, let's say if I want a Q-sec of, let's say 21, then I can have a horsepower, let's take a different value. So let's say I want a Q-sec of 17, then is it okay for me to say that your horsepower should be around, let's say 160? Is that a valid prediction? Any answers? Yeah, perfect, right? So that's a perfect answer. Correlation does not imply causation, right? So we do have evidence for correlation, and we do have evidence that it's statistically significant. But correlation, again, I'll use it in symbols, does not imply causation, okay? This means does not imply. Okay, and hence we can't use the information about correlation to draw any conclusion about or to do any prediction problem. So even if you have correlation, it just tells you that these values are correlated. It does not guarantee that manipulating one will necessarily manipulate the other one. All right. Any questions about this problem before we go to the second problem? Okay, we have. Okay, how do we prove causation? So that's a complete science in itself. And it's currently under very active research. How do you prove causation? So it's probably not part of the course, but let me just give you an intuition as to how would you do that. So one way to test for causation, let me write this in different color because this is not going to be important. So causation, this is optional just to be sure. Okay. So causation can be tested. Okay, this is just one way of doing it, but it can be tested by perturbation. So you can perturb the, so if I have an HP of 160 and it gives me, let's say, a Q-sec of 20, I'll perturb it by a small quantity. So I'll do 160 plus 1 and see in which direction is it going. I'll do 160 minus 1, see in which direction it's going, and so on. Okay, and you'll do this kind of perturbation for multiple rounds. And if you do see it changing in a particular direction, then you can, in some sort of sense, conclude that there is causality. Okay, but it's a completely different science in itself, and it's not as easy as the way I've put it. Okay, but this is the general idea of inferring causality. All right, so move to second problem. In the second problem, you're essentially testing the thesis of regression, which is a very simple idea. So you are given two quantities. Both of these appear to be um, continuous. So father's height. Again, I'm plotting this on the x-axis because that's the independent variable. The son's height is something that we expect to be dependent on the father's height and not the other way around. Okay. You're given this kind of information and you're asked first to calculate the correlation coefficient. The next question that you're asked is what proportion of the variance in the son's height is explained by linear regression of son's height on father's height. And finally, you're asked to calculate the correlation coefficient. Okay, so let me quickly give you an overview of why do we do a linear regression at all. So imagine you have two quantities, x and y, x being independent and this being the dependent. So you're given certain number of data points, which look like, let's say, something like this. What is my task? My task is to figure out the relation, it's the relation, not the relation, but the relationship between x and y. Okay, so imagine you are given this kind of information. Okay, and why do we want to figure out the relationship? In some sense, we want to figure out this relationship so that even for those values of x, let's say if this is a new value of x here on the x-axis, I can predict what value of y should it be. Okay, at this point I don't really know, it could be anywhere on the y-axis. But if I come up with a model, which will essentially help me to guess what this intermediate value would be, right? And why do we care about it? So you can think of this in multiple contexts. For example, in the level of, in particularly in biology, you can think of this X being the amount of drug being administered and the Y being some sort of a numeric quantity which shows how much effect is happening, okay, or how many cells are dying, for example, if you're doing like a chemotherapy experiment. So giving this kind of model will essentially help you to determine what value of Y should be, okay? So how do we do that? So we can start thinking of this in a very complicated fashion. And how do we do that? So one way would be, let me join this line, join this line, this line, this line, this line, this line, and so on. Okay, so this is one model, fair enough. The problem with this model is in order to come up with something like this, I cannot really predict what the other direction would be, right? It's going to be a complicated model in the sense because there's a lot of ups and downs involved. And in a sense, this is not a good model because I can't really use this model for predictions in the future. I might still be able to use it for what's called interpolation to predict anything which is between these 2 points, but I can't extrapolate it beyond this point. Okay, so I don't know which direction it's going to go. So we take a very simplified approach, and we say that the simplest model that I can think of is a simple line. So I'm going to fit a line, and I'm going to fit this particular line here. Let me use a different color so that it stands out. Sorry. So we had a couple of points here. Okay, so I'm going to use this line as a fit. And this model of this line is a very simple model, beta naught plus beta 1 x. Okay, where your intercept is donated by beta naught and your beta 1 is the slope of this line. So what does slope mean? So a slope means essentially this. If the slope is 1, then this is 45 degrees. The slope is 0, that means beta 1 is 0, and all the intermediate values follow. Okay, so slope increases in this direction. Okay, so this is what intuitively it means to these coefficients. Okay, and your beta naught implies how much intercept does it make with the y-axis. Fair enough, but fine. I have a line, but how should I figure out this line? Okay, why is it this line, and why should it not be this line, or why not something like this line? Okay, Well, why not? Because I'm further constraining how I fit this line. I'm further constraining how I create this line. Okay, and the way I'm constraining this is by saying that at each level of x, the difference that I see in the observed value of y then predicted. Okay, so every point that lies on this line is a prediction. Why is it a prediction? Because it has come out of a model. So if your x value was somewhere here, then the corresponding value of y is here. So I call it y hat. This is predicted. Okay, and this predict for this value of x. However, what you're seeing is this value, which is observed. So in essence, I have created some error, right? I've created this much amount of error, which I am going to call my residual. And this happens to happen at each of these points that you have values for. So for every fit that, so for this particular line fit, there is some amount of difference in the observed and the predicted value. This is kind of an example in which there is a residual for each of these values, but it's not always necessary. Okay. So the other constraint that I'm putting when I fit this model is to say that the sum of residual square is minimum. So in some sense, I'm taking the most constrained approach. I'm fitting a very simple model, which happens to be this line. And the way I'm fitting this is I'm saying that the amount of now difference that I see in the predicted values versus what I observe, which is this and this, is minimized. Okay. And that's how you get like a very unique fit. Okay. So this line is a unique fit line. And the only reason it's unique is because of presence of this criteria. It should be the other way around. So this ensures that the line is a unique fit. Okay. Now, one more factor that is something that you need to be aware of is, in a sense, the residual is given by for a particular. So if let me give this. So if y is the observed value, then your residual E is given by y minus beta naught minus beta 1 x. Okay. So this is observed, not predicted. Okay. And that's why this is, so let me write this down. So beta naught plus beta 1 x is y hat, which is predicted. So residual E is essentially observed minus predicted. Okay. One more assumption that goes in behind this linear model is that the residuals are normally distributed. What does that mean? What it means is if I call this residual E1, E2, E3, E4, and if I were to plot them on a number line, then in some sense you will see a normal distribution. Okay, so they are essentially originating from some normal distribution. This is E1, let's say this is E2, this is E3, and this is E4. Okay, so that's kind of the implicit assumption that goes behind fitting a normal model. Now, uh, another fact which is kind of implicit is this assumption about normality is generally not satisfied if both x and y are discrete random variables, or they are discrete numeric quantities. So if x is count and y is count, then this assumption that the residuals are continuous random variables is not necessarily satisfied. Okay, and you can think of why, because your predicted values minus the observed values can often result in pure count values. So there are other methods of regression. This is one way of doing regression. It's called your ordinally. So its name is, let me write this down here. This is called ordinary linear regression. It's the simplest model of regression. There are other ways of doing regression as well. The essence of the regression remains the same. So you're still trying to find a model for, sorry. Okay, let's see. You're still trying to find a model for y versus x. The kind of assumptions that go behind this particular model make it an ordinary linear regression. And those assumptions are the residual summation of your residual squares is minimized and the residuals themselves are normally distributed. Okay. Now, one more thing before we actually solve the problem. And that problem is of how much amount of variance is being explained by this data. So uh, probably use one more figure. So you are given again y values. Okay, so there is some variance in y. I've decided to do a model fitting and I've tried to fit a linear regression model. The moment I do that, I get for each value of my x, so this is x, 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 and one more x. So for each of these, I now have new values of predicted y. So this is y1 hat, y2 hat, and so on. Right? So initially there was some variance in y, and now I also have some variance in y hat. Okay, why is there a variance in y hat? Well, because these values are all different. Okay, so I'm still using the same x, but now rather than using the observed value, I'm using the predicted value. So I can calculate the variance in y hat as well. Okay, now what really is a good model? So good model is something which can explain the variability of y by what variability you see in the predicted values. Okay, so if your variance, let's put it the other way around. So the proportion of variance explained is equal to variance in y hat divided by variance in y. Okay, fine. So this is how intuitively what this means, that I've tried to fit a model and hence I'm going to observe a variance in my predicted values. The proportion between what my original values of y, which is the observed. So just to be clear, this is observed, this is predicted. How is it predicted? By beta naught plus beta 1x. Simple as that. This can also be written in this form: sy square minus se square divided by sy square. Okay. The reason for the origination of this formula is intuitive. So I'm observing certain amount of variance in my y values, which are again the observed values. But the model is also doing certain amount of error. Okay. And this error arises from residuals. So if these residuals were to go to 0, so if SE is 0, what would my plot look like? My plot would look like a perfect line which goes through all the points. So if SE is 0 implies the proportion of variance explained is equal to 1. Okay. There's an alternate formula to calculate this, and that is the simplest formula. So proportion of percentage. Okay, so if I'm talking about percentage, you can multiply it by 100. So let me just be clear. This is also equal to R square, where R is your correlation coefficient. This is also equal to SY square minus SE square by SY square. Okay, so when you're doing the project, one particular question asks you how much amount of variance explained do you see in your information in your data. If you're fitting a linear model, all you have to do is tell me the value of the square of the correlation coefficient. Okay, and you can see in some sense why this happens. This SE equal to 0 also implies, and other way around as well, R equal to 1 implies the standard residual error is 0. Standard error residue 0 implies uh, the correlation coefficient is 1, which essentially implies the line is perfect fit on all the points. Okay, and this doesn't have to be 45-degree. It's also okay for it to be like this. Okay, it can be any slope. The slope does not matter. Okay, so that was a bit of a slide about the entire linear regression. Now, any questions before we proceed? If you understand everything, this problem should be straightforward. Okay, so if there are no questions, I'll start with the first problem. It's very simple. We just plug in the formulas that we saw earlier. Oh, sorry. You're already given all these quantities, and if you plug in the numbers, it will come around to be 0.98. Now, what proportion of the variance is explained? So this is given by sy square minus se square by sy square. You're given all these quantities already. Se is given, sy is given. If you plug in the numbers, this comes around to be 0.96. This is also equal to 0.98 square. Okay. This is something that you got from part A. Okay, so when you're asked to calculate the proportion variance, the simplest idea, if you already have access to correlation coefficient, is to take its square. And finally, we have the 95% confidence interval for beta 1. So this is given by beta 1 value plus minus t 0.025 standard error of beta 1. Fine, but how did we don't have the value of beta 1, but the value of beta 1 is given by sy by sx. So intuitively, how you're calculating the value of the slope is you're adjusting for the amount of variation you're seeing in y. So you're essentially, the higher the variation in y, more is the slope, and you can see why, because the slope essentially quantifies how much difference you're seeing in y. So higher is the variance. So this is in some sense sy, higher will be the value. And the denominator is sx. Again, if the variation in x is very small, this will be a large value. Okay, and you can see again why, because if I control my sx and my sy is fixed, then I need to climb up higher as compared to this. Okay, actually this is fixed. Okay, this is just an intuition. You'll have access to the formula. So if you don't get this part, please tell me and I'll explain again. If you plug in the values, this value comes around to be 0.45. Okay. In a sense, the standard error of beta 1 is given by se by sx. Again, you'll have access to this formula, but you can think about, and again, in the same sense as to why we get the same value. So let me probably just be clear. So this is sy, this is still sy. This is sx, which is small. This is xx, which is larger. Okay. This implies your beta 1 is larger and your beta 1 is small. Okay. Probably not the best way to understand this, but if you have any questions as to what I mean by that, I'll be happy to explain. But for other purposes, you have this access to the formula. Okay. Fine. So we have everything we need. This value will be 0.032, t 0.025 with degrees of freedom equal to 30. If you go to the table, oh, sorry, it's not 30 in this case. The degrees of freedom are 8. So if we go to df equal to 8, which is this line, we are interested in 95% confidence interval. So this value is 2.306. So t 0.025 is 2.306. We have everything. The 95% CI comes around to be 0.38 to 0.52. 0 is not included. Okay, implying that this correlation coefficient, this slope coefficient is significant. All right, final problem. This is kind of the problem that you'll also see in your projects. You're given residual plots and you're asked, is the linear model sufficient to explain the relationship between x and y? So the only condition that we need to satisfy is residual should be randomly distributed, okay, with x if x and y are really linear. Okay, so let's try part A. Anyone wants to take a guess, or like anyone wants to know and know? I mean, anyone wants to tell what their answer should for this should be? Okay. In the meanwhile, you think about it. I have one question from one of the students. Is there a preference of what type of beta one we want, like larger or smaller? Well, so we don't have a preference as such. It's not that we are deciding what beta one should be. Beta one essentially comes from the fact as to how much relationship between you see between y and x. Okay, so uh, one thing that you also want to be, which I actually missed out, was that the value of beta one is dependent on the scale. Okay, so by itself, beta one does not have its entire is not completely interpretable. Okay, it's interpretable in the sense if you know really the scales. So let's take a very simple example. If this is father's height in inches and this is son's height in centimeter. Okay, now in this case, the beta one, I am running out of space. So let's, okay, and this one is, let's say, beta 2. This one is in inches, and is in inches as well. This is son, this is father. Okay, what do you think will happen to beta 2? So beta 2 will be less than beta 1. Okay, assuming we have similar linear relationship. And that's just because the scale of uh, the centimeter, so sorry, it should be the other way around. So centimeters has 1 centimeter is 1 upon 2.54 inches. And hence we expect that the beta 1 slope would essentially be, even though the values are the same, even if I just change the scale, then the beta 1 values will differ. Okay, beta 1 value is essentially telling you how does the other variable scale with respect to the variable on the x. So if it scales by, so if beta is greater than 1, that implies that y scales faster than x. Okay, beta less than 1 implies y scales slower than x. In a sense, it's telling you how much amount of y varies if you vary the value of x by 1 unit. Okay. All right. So move to talking about this problem. We're kind of running short on time now. So A is random, and hence linear model is sufficient. B. B, you see a U pattern. Okay. This pattern is kind of very common, and this generally implies that linear model is not sufficient. Why? Because the linear model, the model between y and beta, sorry, y and x should have square terms, okay? Because you see like a parabola term, like a square relation, okay? You'll not be asked to explain what this pattern is. You're just asked to explain whether this is sufficient or not. And the only criteria I'm going to use is the particular pattern random or not, okay? So this part is extra. C, again, we have, okay, what do people think about C? We are already out of time, but if you want to take a guess, what's happening in case of C? Okay, so in C, also we have increasing pattern. That also means that linear model is not sufficient. Okay. One possibility for this is to add more variables to the model, which is called multivariate regression. Again, this is extra. You don't have to know this, but just be aware that you might see a similar pattern when you're doing your analysis of the residuals. Okay. So in some sense, it's increasing with the value of x. And it just also means that variance of x is, sorry, variance of y with x is not constant. Okay, you have higher values of the residuals for higher x, essentially implying there is higher variance in the values of y, which you can also see here. Okay, there is a lot of variation as the y value. So this is high variance in y. You can see it on the plot here as well. Whereas here you have low variance. Okay, these are all asides. You don't have to really write all this down. We only expect you to be able to figure out whether the linear model is sufficient or not. Okay, so we are already out of time. However, if there are any questions, I'm happy to take them. Let me stop sharing. Okay, if there are no questions, you're free to go. Please make sure you turn in your project in time. The project is due on 28th April. It's due well before your exams, and we don't want it to overlap with your exams. So make sure you turn this in time. Okay. All right. Everyone, have a good week and stay healthy. Okay. All right.